Hi students, today we are going to see the preparation of pyridine derivatives. So here it is from the Hantzsch synthesis of pyridine derivatives. In the last class we have seen the synthesis of pyrrole, furan and thiophene from 1,4-diketones. So here we will see the Hantzsch synthesis for the pyridine derivatives. So I have written the statement of this synthesis on the board, that is the condensation of a beta keto ester with an aldehyde and ammonia, and it produces a dihydropyridine derivative, which on further oxidation with nitric acid will produce a nitro derivative. So we will produce a pyridine derivative. We'll see this reaction, and it is one of the very important question for your exam. So those the preparation of those 3 5-membered heterocyclic rings from 1,4-diketones will ask in for 2 marks. So this question usually asks for 4 or 5 marks. So we also have a small mechanism of this reaction also we are going to discuss in this chapter. Usually for preparations we do not need to write the mechanism, but many of the times this question has also used to be asked for 5 marks. So that's why we'll also discuss the mechanism of the reaction. So I'm going to take, here we are taking 2 moles of beta keto esters, 2 molecules, and one aldehyde and ammonia. See here, CH3, CO, CH2, CO, OC2, H5. So it is one of the beta keto ester. So this is COOR. Okay, COOR. This is ethyl group. This is an ester group. This is an ester group, and alpha position. This is beta position. At beta position we have a ketonic group. So this is an example of an beta keto ester. Beta keto ester. You already know the name of this compound because it has come in your enolate chapter. So this is EAA, ethyl acetoacetate. Ethyl acetoacetate. EAA. It is one of the very good reagent for most of the organic synthesis. This EAA and DEM, diethyl malonate, those 2 compounds you have studied in the synthesis via enolates method. So yeah, this is an example of beta keto ester. It is, here we have taken 2 molecules. It is going to react with an aldehyde. Let me take the aldehyde CH3 COH. This is acetaldehyde. Okay, and ammonia, NH3. So all these 3 will get condensed, and it is going to give us a dihydropyridine derivative, ammonia. Okay, dihydro. So usually condensation means by heating. Condensation means heating with removal of water. That we'll see in the mechanism. So here, yeah. So nitrogen, CH3, CH3, COOC2H5, and ester. Here also COOC2H5 and ester group. Here also CH3 and double bond H. So this is a dihydropyridine derivative. Dihydropyridine derivative. So why it is called dihydropyridine? Because in the case of pyridine, usually there is no hydrogen, but here is an extra hydrogen. Here also one extra hydrogen. So there are 2 hydrogens. We have to remove this hydrogen, and that will be done by the oxidation actually. So that's why it has having a 2 extra hydrogens in the pyridine. And also that's why it is dihydropyridine molecule. So as usual, which further undergo oxidation with HNO3. Okay, it is undergoing oxidation. So now it will produce a pyridine derivative. So here removal of H2, dehydrogenation. Dehydrogenation is also known as oxidation. So removing this hydrogen and this hydrogen will give us a pyridine derivative. So this will be the pyridine derivative. CH3. Okay, this is the pyridine derivative. So now you can see the complete pyridine cycle ring. Okay, pyridine derivative. Okay, so pyridine derivative. This process is given by the Hantzsch, German chemist. So you can remove all this ester group also by hydrolysis and decarboxylation. So those also can be removed. So usually this hydrolysis and decarboxylation will be done when we treat with base and calcium oxide. These are good reagents. Okay, for hydrolysis, basic hydrolysis with decarboxylation by heating. So here we are going to form CH3, CH3, CH3. Yeah, an alkyl derivative of pyridine. Alkyl derivative of pyridine. Okay, this is we can get from this hand synthesis. If you name this one 2, 4, 6. Okay, at second position, fourth position, and sixth position we have a methyl group. So then it is 2, 4, 6 trimethyl pyridine. So this much we can get from the hand synthesis. So no direct formation of the pyridine. It will first form a dihydropyridine, and on oxidation it will forming a pyridine derivatives. So it is one of the very important method we have in our syllabus for 4 marks or 5 marks. Okay, so it's very simple. 2 moles of EAA, beta ketoester, will condense with aldehyde and ammonia, forming first dihydropyridine derivative, which upon oxidation give pyridine derivative. So this is also pyridine derivative. So here we have removed just that ester groups by hydrolysis and decarboxylation. Okay. Yes. Many times its mechanism has been asked. So now let us see the mechanism of this synthesis. If you see the mechanism of this reaction as the synthesis, Hantzsch synthesis of pyridine derivatives, we can make it in 3 steps. So let me write the first step where this beta ketoester condense with the ammonia. Okay, so here CH3, this is EAA. Okay, so this is a ketonic group. So by the internal proton transfer, this ketonic group can be converted into the enolic form, which is an isomer of this same compound, that is ketoenol tautomerism. So by ketoenol tautomerism, this aldehydic group, sorry, this ketonic group will convert into an enolic group. So then it will become CH3, COH, this become double bond now, CH, CO, COC2H5. Okay, this is the same EAA, but it is in enolic form, same EAA, it is in ketonic form. Ketonic form. Okay. So this enolic form, when it is treated or condensed with ammonia, usually ketones when react with ammonia, the condensation product will be the imines. So here let's just substitute. So then it will be easier for us to understand. Okay. Here this ammonia will be NH2 minus and H plus. Okay. This is usually NH2 minus and H plus. This just I'm just replacing this NH2 minus and OH minus will be replaced by this NH2 minus, and here this OH minus and this H plus will be eliminating as water. That is also a condensation. So by eliminating water, I'm going to get CH3 C NH2 double bond CH CO OC2 H5. Okay, just it's like a substitution, but it is actually a condensation. We have removed water, and I just made it easier for you to understand. So that's why enolic form of the EAA has been taken. Okay. Yeah, this is, let me call this as EA. Okay. And in the second step, okay, this EAA molecule will be condensed with aldehyde. Okay, we have taken an example of acetaldehyde, CH3 COH, acetaldehyde. Now it is going to condense with this EAA. CO CH3, see, CH3CO CH2 CO O C2H5. Okay, this is also same compound EAA. So when these compounds both undergo condensation, so here this oxygen and H2 will be eliminating water. So now both will get condensed. Let me write that compound. CH3 CH double bond C O CH3 O C2 H5. Okay, this condensed product, or the condensation product, let me write it as B. Okay, this one I call it as B. So now what we do, now will both A and B will react, and it is going to form the products. Okay, so can I start from there? Yeah, here. This is about step 1, step 2. I think just let me have all the steps on the board, because we can easily get it later. So if I come to the step 3, so here A and B are reacting. Okay, so let me write that one. So A here, so I will take from here, first we'll take the COO C2H5, this whole COO C2H5, COO C2H5 ester group, which is attached to the CH. So CH double bond C NH2 and CH3. Okay, this is A, right? A. Now it is treated with B, this compound. Okay, so here here also I'll take that ester, this group here. Okay, COO C2H5, this whole group, which is attached to a carbon. This carbon is attached to a ketonic group. So let me take that ketonic group, COCH3, and this carbon is with the double bond with this derivative, ethyl derivative. So double bond carbon, here we have a hydrogen, and this is linked with CH3. Okay, CH3. Yes. Okay, this is B. See, COO ester group, COOC2H5, that is linked to carbon, that is linked to double bond with the CH3, CH3, and below COCH3. Okay, this is B. So now here the nitrogen is the 3 bonds have a lone pair of electrons. The reaction will start from here now. So this nitrogen will give its electron to the next bond. It becomes a double bond, and here the electron density and this carbon increases now. So that's why this carbon increases. So that's why it will be attacking the carbon of the next bond. So now this carbon has got that electrons. So electron density and this carbon increases. So this carbon increases. That's why this will give electron. So this carbon, now this electron density and this carbon increases. Carbon, as you know, electron cannot be held by the carbon, so that's why it will shift to the oxygen. Okay, so now we get this product. Let me write that compound, and the both will get now condensed. Both the compound will become one compound. COO C2H5 CH here. Here it becomes single bond, C double bond, NH2. So 4 bond for NH, that's why it gets the positive charge, CH3. Okay, and this CH will attached with another CH that is linked with CH3. So it is linked now with a single bond to carbon. Here it is ester group, COO C2H5. Now it became a double bond, carbon, oxygen with minus charge, and CH3. This is what happened here. Okay, so here nitrogen is having positive charge. So as you already know, nitrogen cannot hold that positive charge because it is an one of the most electronegative element. That's why this oxygen will give back these electrons, and electron density and this carbon increases. That's why these pi electrons will abstract this proton. So when these electrons will be given and the proton has been taken, so this electrons will have been abstracted the proton, so it becomes double bond now. So the electron density and this carbon increases, so that's why these give back those electron to the nitrogen. Okay, the first oxygen minus charge will give an electron, it becomes double bond, so electron density and this carbon increases. That's why the pi electrons will abstract this hydrogen, so this hydrogen will shift to the this carbon. Okay, to this carbon hydrogen will come, and this become a double bond, and this electron get back to the nitrogen. Okay, so let me write that structure. Okay, COO C2H5, this becomes carbon only now. A proton has been abstracted by the another pi bond, CH3. This is C. Here an H has been come. Okay, COO C2H5. This became double bond, carbon, NH3. Okay, again it gets this lone pair, CH3. Here now it becomes single bond, oxygen. It again become double bond, and CH3. Okay, now cyclization takes place. Okay, now there is a cyclization. So this is not cyclic now, it is going to form a cyclic structures. So these lone pair of electrons will now like this carbon atom. So this carbon is having a delta positive because it is attached to link to the most electronegative element like oxygen. So when these electrons are attack this carbon, these electrons will shift back to the hydrogen, but not easily these electrons are going. So one of the hydrogen has to be eliminated. So it will be start with the hydrogen. So this hydrogen has been given electron to the nitrogen. So then electron density in the nitrogen increases. Hence those electrons will shift it to this electropositive, so are the electron deficient carbon, and these electrons will shift to the oxygen. So, and this proton will be shift to the this oxygen now. This become OH. Okay. So from hydrogen has been shifted, proton shifted from nitrogen to oxygen. Okay. So let me write that structure. CH3, C. Here there is an H. Yeah, sorry, I forgot H. This is CH, COO, C2H5. It is single bond. Here it's single bond, carbon. Here COO, C2H5. This is a double bond, carbon. This NH, okay, is going to form a bond with this carbon, and here this oxygen become OH along with CH3. Now also our nitrogen is having 3 bonds, so that's why it is lone pair has been given. So both now nitrogen is also become stabilized. So now there is a elimination of water molecule, we'll see. So this hydrogen will give its electron as eliminated as proton, and electron density on this carbon increases. That's why it eliminates this OH molecule. So then it is the, here there is CH3, sorry. So hydrogen is proton elimination with the elimination of hydroxide. Both will eliminate as water. Water. Okay. So let me write the remaining part. CH3, CH, C, COO, C2H5. This hydrogen has been removed. So C, this become double bond. Oxygen is also removed. Only CH3 is retained. So it is single bond. NH. Okay. From here, carbon. Here also COO, C2H5, an ester group. Here it is double bond and bond, and this carbon is with CH3. Okay, this is nothing but our first product, that is dihydropyridine derivative. Yes, this is the dihydropyridine derivative. Okay, as further you already know, this dihydropyridine derivative will undergo oxidation with nitric acid, which will give us pyridine derivative. Okay, let me write that one. Yeah, so now this compound will be undergoing oxidation with NH3. So oxidation means here this hydrogen and this hydrogen has been eliminating. Okay, that dehydrogenation is also known as oxidation. So now this hydrogen will give electron, so it become double bond, electron density, and this carbon increases. That's why these electrons will be given to the this bond, and this become a double bond. And of this hydrogen, okay, this hydrogen will be eliminating with this electrons. Have a come in ulta manner. Yeah. So both same. This hydrogen will give electron. This will shift here. Yeah, though both okay. Okay, sorry. So one of this hydrogen will give electron. It becomes double bond. The electron density and this carbon increases. It gives to the nitrogen, and this further this hydrogen will be eliminating. Okay. Okay. Somehow it is dehydrogenation. Yeah. C, CH3, C, C, N, C, C, N. Okay. This become double bond, this become double bond, this is also double bond. Pyridine ring has been come. Here we have an ester group. Here we have a methyl group. Here also we have a methyl group. Here we have an ethyl ester group. Okay, this is the pyridine derivative. This is actually the product, pyridine derivative. But further, we can remove these ester groups by hydrolysis and decarboxylation. So let me write that also. So first it undergoes hydrolysis, and second one it undergoes decarboxylation. Okay, now it is going to form a trimethyl pyridine compound, CH3 C C H, it become double bond C CH3, here nitrogen, a double bond C CH3, single bond. Okay, here double bond. Both are same, giving the same product. Okay, here it is a double bond, carbon, hydrogen, oh, bond. You know, in the hydrolysis, these esters will be eliminating as carboxylic acid and alcohol. Okay, and in the decarboxylation, there is a removal of the CO2. Only hydrogen is retained. That hydrogen I have written on this board. So now it is the pyridine. So that pyridine name is 2, 4, 6 trimethyl pyridine. This is the product we can get from the Hantzsch method of synthesis for the pyridine derivative. Okay, this is how this reaction or the synthesis would happen. Okay, so we can classify this into 3 steps. In the first step, the enolic form of the EAA, beta ketoester, will condense with ammonia and forming a intermediate A. Okay, and the aldehyde will condense with this ketone, that is beta ketoester, and forming an intermediate B. Both intermediate A and both B will react. So there is a here the nitrogen has given electron, and these electrons shift to the carbon, and further electron shift to the oxygen. Okay, and the oxygen give back that electron, and this pi electrons abstract this proton. Here nitrogen has got a positive charge, that's why it has happened. So further the cyclization has to take place, because this is not, two compounds has to get cyclized. So here this hydrogen has given electron, and there is cyclization takes place. This hydrogen is shifted from nitrogen to oxygen, that is internal proton transfer. So this we get. Okay, here there is a removal of this water molecule, will give us a dihydro derivative of the pyridine, and this dihydro derivative of the pyridine has an extra hydrogen at the nitrogen and the carbon number 4 that has to removed, and that forming a complete aromatic cycle, and that will be the pyridine derivative by the dehydrogenation or the oxidation. Okay, this product is enough to write, and here we can also remove esters easily. So methyl group removal is difficult because demethylation we don't have any process, so that's why we can remove these esters by hydrolysis and decarboxylation. When we remove esters by, when hydrolysis takes place, these esters will convert into alcohol, will be eliminating, and this will become a carboxylic acid group. And by the decarboxylation, this there is elimination of CO2, hence it will forming an any hydrocarbon, that is forming a pyridine derivative. So here there is elimination of 2 molecules of C2H5OH ethanol, and also 2 carbon dioxide. So that you can write or not, it depends. Okay, this is how the process takes place. I hope you understand. And for this mechanism, you only need to practice. You write it for 2-3 times, then it will be the very simple mechanism it is, but it has a long many steps. Okay, the steps are more, but the process is very simple. Okay, this is one of the synthesis for the pyridine, that is by the Hantzsch, a German chemist. So I think you got it. Please write it, and then you take it down. So if you practice only, then it will be yes, as practice makes man perfect. So you need to practice, write this procedure, this mechanism. Then only you can get it. Okay. Thank you. Thank you for watching videos, and please like it and subscribe to my channel and share with your friends. Do not forget. Thank you. You can take the screenshot. Thank you.